In the last lecture, we were trying to get a physical understanding of the vector derivatives, the gradient and the divergence. The gradient of a scalar field is defined as follows. If I am at a particular location x vector where the underline represents a vector. Okay. So, this x vector is equal to x E x plus y E y plus z E z. Okay. And if I move a small distance away from this location, okay, delta x vector, to the new location x plus delta x vector, okay, where this delta x has the displacements delta x E x plus delta y E y plus delta z E z. Okay. Then the difference in a scalar field, okay, a concentration say between the locations x plus delta x and x, okay, can be written as c at x plus delta x minus c at x is equal to delta x times partial delta x dotted, okay, delta x vector dotted with grad c, okay, where grad c is equal to E x partial c by partial x plus E y partial c by partial y plus E z partial c by partial z. Okay. Though I have written the gradient in terms of its component, the gradient is actually a vector at this point, okay, which has a particular magnitude and a particular direction. Okay. And that magnitude and direction is independent of the underlying coordinate system that is used to analyze the problem. Okay. It is independent of that. The gradient vector of a field at a point has a particular magnitude and direction. The components of that will depend on the coordinate system, but the magnitude and direction are real physical quantities which are independent of the coordinate system that is used to analyze the problem. Okay. So, this is the definition of the gradient. Okay. Now, in some other coordinate system, okay, if I had a coordinate system x a, x b and x c as the coordinates r theta phi say, with scale factors h a, h b, h c, okay, with scale factors h a, h b and h c, then this delta x vector is equal to, okay, h a delta x a E a plus h b delta x b E b plus h c delta x c times E c. Okay, that is the vector displacement, where delta x a, delta x b and delta x c are the increments in the coordinates, and h a, h b and h c are the scale factors required to which render this differential displacement to have unit of length. In that case, it is quite easy to see that once again this relationship will hold, okay, this relationship will hold provided the gradient is defined as grad c is equal to 1 by h a partial c by partial x a E a plus 1 by h b partial c by partial x b E b plus 1 by h c partial c by partial x c E c. So, the differential displacement in a curvilinear coordinate system is H A delta x a times E A, where E A is the unit vector, plus H B times delta x b times E B plus H C times delta x c times E C, okay, where E A, E B and E C are perpendicular to each other in a orthogonal coordinate system. Delta x a, delta x b and delta x c are the increments in the coordinates, and H A, H B and H C are the scale factors which result in delta x vector having the dimension of length. The gradient in this case is defined as grad c is equal to E A by H A partial c by partial x a plus E B by H B partial c by partial x b plus E C by H C partial c by partial x c. Okay, so that it has dimensions of concentration divided by length. And if E A, E B and E C are orthogonal, you can easily verify that grad c dotted with delta x will be equal to the difference in concentration at the locations x and x plus delta x. Okay, so that is the definition of the gradient for a curvilinear coordinate system. Grad c is a vector and it is defined uniquely at each point in space, and at a given location x, okay, if I travel equal distances, okay, equal distances delta x magnitude, okay, in different directions. Okay. I told you that the change in concentration will be a maximum when grad c and the displacement vector are in the same direction, because their dot product is equal to the product of the distance times the gradient. Okay. So, grad c is along direction of maximum variation in C. Okay. And if I travel along a direction that is perpendicular to grad C, then delta x vector dot grad C will be equal to 0. Okay. So, if I travel along a direction that is perpendicular to this gradient vector, then delta x dotted with grad C will be 0. Okay. And that implies that gradient is perpendicular to surface of constant C, because the change in concentration is going to be 0 if you travel along the direction perpendicular to grad C. Okay. So, the gradient is perpendicular to a surface of constant C. Okay. And I had derived for you the integral relation for the gradient. Okay. If I have 2 points A and B along any path relating connecting A and B, if I define a differential displacement as delta x vector along this path, the integral relation is that integral, okay, dx vector dot grad C, okay, between A and B is equal to the concentration at the location final location x b minus the concentration at the initial location x a. Okay. So, that is the definition, that is the integral relation for the gradient. This implies that this integral of dx, the differential displacement vector dotted with the gradient of C at that location, integral of that between any 2 points has to be the same independent of the path that is taken between these 2 points. And along a closed path, if you go around and come back to the same point, since the initial and final points are the same, the term on the right side of this equation is equal to 0. Okay. That implies that integral of dx dotted with grad C is equal to 0. Okay. Yeah. The second was the divergence. Okay. This was defined for a volume. Okay. If you take any volume, differential volume delta V about the point x, okay, the surface of that differential volume is S. Okay. The differential volume surrounding around the location x is S, and the unit normal, outward unit normal to this is equal to n. Okay. The definition of the divergence, okay, divergence of any vector. Okay. I think in the last class we had used a vector j, okay, for the flux. Okay, so I will just use that. Divergence of the flux vector j is equal to del dot j. Okay. It is equal to integral ds of n dot j outward unit normal dotted with the flux vector divided by delta v in the limit as delta v goes to 0. Okay. And this, so at the location x, you find out what is the flux on a surface S surrounding a differential volume delta V, dot the unit normal with the flux, integrate over the surface and divide by delta V, and you get the divergence of the flux. Okay. So, this is how you calculate the divergence. Okay. The divergence has dimensions of 1 over length, because it is integral surface integral divided by delta V, and in the limit as delta V goes to 0, as it shrinks to a point, the value of the divergence is independent of the volume delta V that is used. Okay. You can use any volume, the value of the divergence will be independent of that volume, and it is only a function of the position. Okay. So, it is a single valued function of position at that location. Okay. And this was equal to the net flow rate out of the volume, okay, divided by the volume itself, okay, the divergence of the flux. Okay. The divergence of the flux, if you recall, this was equal to the net flow rate, okay, integral ds n dot j. Okay. The flux is the transport of mass across the surface per unit area per unit time. Okay. Transport across the surface per unit area per unit time. The flux dotted with the unit normal is the transport perpendicular to the surface. Okay. The flux dotted with the unit normal is the transport perpendicular to the surface. Okay. It is positive if j is along the outward unit normal, and it is negative if j is along the inward unit normal. And integral ds of n dot j is the total flow rate out of the differential volume. Okay. It is the flux dotted with the area. Flux is mass transported per unit area per unit time. Therefore, integral ds n dot j is the mass transported out of the volume per unit time, that divided by the volume itself. By the volume itself in the limit as the volume goes to 0. Okay. Okay. The divergence of the flux is the net transport rate out, okay, of this differential volume divided by the volume itself in the limit as the volume goes to 0. Okay. And this divergence is literally the divergence. Okay. So, for example, if I had a net flow out of this volume, okay, if I had a volume in which there was a net flow out, okay, the divergence of the flux would be positive, because there is a net flow out of this volume. Okay. In contrast, if I had a differential volume in which there is a net flow in, okay, this integral of j dot n, the flow rate in would be the flow rate would be inwards. Therefore, j dot n will be negative, and the divergence of the flux will be negative. Okay. So, this is literally the divergence. If a flow field diverges outward from a point, okay, That is, if I had a flow field, okay, I have some flow field, let us say some flux distribution. Okay. I go to a point and I find out the difference between the flux at that location and the flux at the center. Okay. If that difference on average is outward, okay, so that the field diverges from that point, the divergence will be positive. If it is inward, it will be negative. And for a field which is on average neither inward nor outward, when the total amount of mass transported out of that volume is 0. Okay. You could have, for example, inward flux on some parts of the surface and outward flux on the other part. If the net transport rate is 0, then the divergence will be 0. Okay. So, that is the physical meaning of the divergence of a vector at a point. Okay. It tells you whether the vector field relative to that point at nearby locations is in total outward or inward. Okay. If it is outward, there is a positive divergence. If it is inward, there is a negative divergence. Okay. And this divergence, okay, so okay, is equal to integral of the surface area. Okay. So, if I had a curvilinear coordinate system, for example, okay, in which the coordinates are x a, x b, x c, and the scale factors are h a, h b, h c. Okay. And the unit vectors are E a, E b, and E c. Okay. Now, if I constructed some volume, okay, I will take a cubic volume for simplicity, but you could take any other volume. Okay. For the surface that is perpendicular to the E a direction, for example, for the surface perpendicular to the E a direction, right, the two coordinates perpendicular to the E a direction are in general h b and h c. Okay. Therefore, the surface area is h b times h c. Okay. This ds is h b times h c times the component of the flux along the a direction. Okay. So, therefore, integral ds, okay, of n dot j, okay, is equal to h b, okay, delta x b, okay, into h c delta x c into j a, okay, the component of the flux in the a direction. Okay. And this divided by the total volume, that is h a, h b, h c, delta x a, delta x b, delta x c. Okay. This is being summed over the surfaces perpendicular to the E a direction. Okay. So, okay, you have surfaces at which have a unit normal minus E a on the left and E a on the right, and basically you are subtracting this over these two surfaces. Okay. And it is relatively easy to see that at the end of this you will get 1 by h a, h b, h c, okay, partial by partial x a of h b, h c, j a. Okay. Go back and refer to the calculation of the spherical coordinates, okay, in order to get this result. Okay. It is quite easy to get. The delta x b and delta x c will cancel out with the numerator and the denominator. The h b and h c are in general functions of x a. Okay. Therefore, I take the derivative of h b h c times x a. Okay. And in the other directions I will get partial by partial x b of h c h a j b plus d by dx c of h a h b j c. So, this is the expression for the divergence in a curvilinear coordinate system. Okay, and that is because it is the integral over the surfaces of n dotted with the unit vector, okay, perpendicular to the surface, outward perpendicular to the surface, divided by delta v. Okay. The integral theorem for the divergence, okay, divergence theorem okay, states that if I had a volume V, okay, with surface S, in which some field was defined, okay, in which some field was defined. Okay. And the field variable, the vector was field variable was uniquely specified at each location. Vector field variable could be a flux, a velocity, or any other vector quantity, which is a unique function of position. Okay. Then the divergence theorem states that integral over this volume, okay, of the divergence of this vector, okay, I will call that, let us just call that as the flux. Okay. This is equal to integral over the surface surrounding the volume of ds of n dot j, okay, where n is the outward unit normal. At the location on the surface. Note that this applies to a macroscopic surface. Okay. This applies to a macroscopic surface, not to a differential, I am sorry, a macroscopic volume, not a differential volume. Okay. So, this divergence theorem applies to a macroscopic volume, not a differential volume. Okay. Now, how do we derive this? Okay. So, let me just expand this out a little bit. So, I have a volume, okay, okay, and a surface S, okay, and I have to prove this relationship for this entire volume and its bounding surface. It is a surface that surrounds this volume. Okay. So, how do you do that? I divide this into a small number of a large number of differential volumes. Okay. Okay. I can label it as index as 1, okay, 2, etc. Okay. And two typical volumes that I will take, okay, volume n and n minus n plus 1. Okay. So, this total volume V, okay, is divided into delta V I for I is equal to 1 to n. Okay. The total number of volumes I goes from 1 to n. Okay. So, if I take two typical volumes, okay, over here, okay, I have one volume here, let us say, okay, delta V I, and the second volume delta V I plus 1. Okay. And since these are differential volumes, I can use the definition of the divergence. Okay. I can use the definition of the divergence of J, okay, okay, into delta V I is equal to integral over the surface of volume I, okay, ds, okay, n dot j. Okay. This is the definition of the divergence for a differential volume. Divergence was defined as integral over the surface S of n dot j divided by delta V. I am applying this to each differential volume within this larger volume, delta V I times divergence of j at that location. Okay. This is the divergence of j at the location x I. Okay. Similarly, for the volume I plus 1, I can write divergence of j at the location x I plus 1 times delta V I plus 1 is equal to integral S I plus 1 ds n dot j. Okay. Now, you know that at a fixed location the vector is uniquely specified. Okay. So, on the surface, okay, that is separates volume on the internal surface that separates volume I and I plus 1, the flux at that location has to be uniquely specified. Okay. The internal surface that separates I and I plus 1, the flux at that location has to be uniquely specified. Okay. However, for the volumes I and I plus 1, the unit normals are in opposite directions. Okay. The outward unit normals for the volumes I and I plus 1 are in opposite directions. Okay. Therefore, n dot j summed over the surface separating I and I plus 1 adjacent volumes, that has to sum to 0. Okay. So, this contribution to the dot product of the unit normal and the flux for adjacent volumes sums to 0, because the flux has the same value on because it is the same physical point in space on that surface, whereas the outward unit normals are in opposite directions. And this sums to 0 for all volumes that are internal, that separate two differential volumes within this volume V. Okay. If I sum the left hand side over all volumes, okay, what I will get is integral dV, okay, of the divergence of J, okay, divergence of J, okay, over this entire volume V. Okay, that is what I will get. On the right side, the contribution to n dot j over all internal surfaces sums to 0, and only thing that I get on the right hand side is integral over the external surface S, okay, n dot j. Okay. And that is the integral relation for the divergence. Okay. Okay, that is the integral relation for the divergence. Okay. That the integral of the divergence of J over the entire volume over any volume is the same as integral over the surface surrounding that volume of the outward unit normal n, okay, of the outward unit normal n dotted with J. Okay. And so, this is called the divergence theorem or the Green's theorem, okay, and it has a corollary. Okay. And that is that if I want to find out the integral over a volume of the divergence of some vector quantity, I do not need to know the value of that vector quantity within the entire volume. It is sufficient to know the value on the surface. Okay. And this integral divergence of J over the volume basically tells you the net rate of transport out of that volume. If J is the mass flux, mass per unit area per unit time, del dot j integral over the volume is the total mass leaving the volume per unit time, okay, which is the same as the right side. Okay. So, this will be positive if there is a net mass flow out of the volume, it will be negative if the net mass flows into the volume. Okay. So, that is the definition of the divergence. Okay. It is literally the divergence at a given location. It is the integral over the surface of n dot a vector divided by delta v in the limit as delta v goes to 0. It assumes a unique value which is independent of the volume that you take. Positive if there is a divergence of the vector field relative to a central location. Negative if there is a convergence towards that, okay, and 0 otherwise. This is the general relation for the divergence. Okay. For an orthogonal coordinate system where the 3 unit vectors are perpendicular to each other, and the divergence theorem states that integral over the volume of the divergence of J is equal to integral over the surface of the unit normal dotted with J. Okay. So, those are the definitions of the 2 vector derivatives and their integral relations, which are independent of coordinates used. Okay. They have unique values at a given location, which is independent of the underlying coordinate that is used to analyze the system. So, this is a physical understanding of the operators that we had used in the conservation equation, okay, plus the divergence of velocity times c is equal to minus the divergence of j plus s. So, these quantities here are the divergence operators, okay, and the gradient is in the constitutive relation. Okay, so this is the gradient. So this is for heat and mass transfer. I will continue and go on to momentum transfer in the next lecture. Okay. The momentum transfer are the mass and momentum conservation equations, also called the Navier-Stokes equations for a Newtonian fluid in the incompressible limit. I will start the discussion in the next lecture. I will see you then.